Michael Moorehead is our next contestant. Michael is an advanced nuclear materials scientist in Irradiated Fuels and Materials, C610. Let's welcome Michael to the stage.
So thank you, JR. My name is Michael Moorehead, and today my goal is to convince everyone that metallurgy is like baking a cake. And the reason that is because when you go to bake a cake, the first thing you do is you go to your pantry, and regardless of what kind of cake you're baking, you look for the same sort of ingredients: your flour, eggs, water, oil, chocolate, and you mix these all together and you heat them up. And at the end of the day, hopefully, if you got the ratios right, you have something that you can eat. Now, when it comes to metallurgy, rather than going to the pantry, the first thing that we do is we instead go to the periodic table and we select the elements that we want. We mix them together and we heat them up and hope that we have an alloy that performs like we want it to. However, in comparison to baking a cake, making a new alloy is a little more difficult. We have to go to higher temperatures. It's harder to get the starting ingredients. They're not exactly on the shelf. And we have to make sure that everything plays well together. And it can be very difficult to make these alloys, and it takes much more time and energy, such that rather than all these great cake recipes that we currently have, often most of the alloys that we have are primarily one ingredient or maybe two ingredients. So we have our iron-based alloys, our aluminum alloys, our titanium alloys, which is kind of like having a cake that's 70% flour or 90% eggs. And so there's many other combinations of these elements that we have yet to be able to explore. And part of that is because they're difficult to make. And even once you make them, you have to go through the process of characterizing them. And rather than just a cake where you can take a bite into it, most alloys you can't get useful information out of that way. We have to instead section them, and we have to polish them, look at them under the microscope, and it takes much more time. And so this is one of the reasons why I'm interested in accelerating the search for different alloys using, in this case, parallelized electric field assisted sintering. So this is one of the techniques that we use to make alloys. Electric field assisted sintering is basically where we smush some metal powders between two punches and we heat them with electricity and pressure. And doing that, we can consolidate our mixture of powders and to make an alloy. And this is good. We can make an alloy. It's faster in some cases than melting it, but it still is relatively slow. And so one of the things that I've been working on is developing a new methodology and some custom tooling that allows us to make many different little cakes at once. In this case, cupcakes. So what we can do is we can take in our cupcake tin and put different combinations of metal powders in each of them and heat them up and consolidate them all at the same time. Now, much like cakes of different compositions will rise at different rates, these alloys will densify at different rates. And so we can't just have a mated set of tooling that pushes on them all evenly, because some of them won't want to push yet and others will need to go much further. And so instead what we do is we put a filler material on top that can move around and apply pressure evenly to all of our little metallic cupcakes. And so at the end of the day, when we smush this all together and heat it up, we can produce these alloy arrays that now have almost 20 samples on them at a time. And so we already have a large factor of savings there on the synthesis, but now you also have all of your alloys on these nice convenient plates that you can then shuffle around to where you need to polish, to where you need to put them under the microscope. And in doing this, we're able to explore all those other combinations and hopefully find some alloys that perform better than what we currently have available. So next time you're experimenting in the kitchen, you can remind yourself that the folks at INL are doing the exact same thing in trying to develop the next generation of materials to power our clean energy future. Thank you.